Hey students, this is a lecture on section 14.7, which is about extreme values and saddle points. So extreme values should be familiar from Calculus 1 and maybe Calculus 2. But remember, when we were finding extreme values, they were local maximum, local minimum, but they were functions of one variable, so they were just a function of x. Well, now we're going to be finding extreme values, which are local maxima, local minima, for functions of two variables, f of x comma y. So I'm not much of an artist, but this is my sketch of a picture of a, f of x comma y. A local max is going to be looking like a hill, and the very top of the hill is your local max, whereas a local min is going to be looking like an upside down hill or a valley, and each of those are local mins. So they're called local because locally around there, they're the lowest point, or local max, locally, that's the highest point. All right, and then a new type of extreme value that you might not know about is when you have functions of more than one variable, you can have what's called a saddle point. And that's what I have sketched over here. And as you can see, the reason it's called a saddle point is it kind of looks like a saddle. And it's called a saddle point because if you notice, if I go along this way, it's actually going to be a local maximum for that variable. So let's say that's x. Whereas if I go along this way, along this edge, it's actually a local minimum for the other variable. So that could be for y. Okay, so it's actually a local max for one variable and a local min for another variable. So since it's not... since it doesn't match up, we call it a saddle point. So that's just where one variable attains a maximum and another one attains a minimum at the same point. Okay, and then those are the three types of extreme values. Actually, technically a saddle point isn't an extreme value, but it gets grouped with them because you still find it the same way. And the way you find extreme values and saddle points is by finding the critical points. And the critical points are where your partial derivative with respect to x and your partial derivative with respect to y are both equal to 0. Okay, so what we're going to be learning about here is called the second derivative test. Okay, so the second derivative test is actually somewhat like the second derivative test from Calculus 1. And in order to be a critical point, your x derivative and your y partial derivative both have to equal 0 at that point. Okay, so partial f partial x and partial f partial y both have to equal 0 at a point, and then it's a critical point. Okay, so when you're doing these problems, the first thing we're going to be doing is we're going to calculate all the critical points by finding the x derivative and the y derivative and setting them both equal to 0. But then if you look at those critical points, you can use the second derivative test to determine whether the critical point is a local max, a local min, a saddle point, or the test is inconclusive, which means we don't know what kind of point it is. Okay, so let's go through all these cases. Okay, so this for calculating the second derivative test, obviously you're going to have to first calculate all the second derivatives. Okay, so first of all, you're going to need f(x(x), which means the second derivative with respect to x. And then, for these first two cases, you have a local max at a point if f(x(x) is less than 0 and this whole thing is greater than 0. So this big mess here, this is called the discriminant. And the reason it's called a discriminant is it allows you to discriminate which type of critical point it is. Okay? So for your discriminant, if your discriminant is greater than 0 and f(x(x) is less than 0, then you have a local max. If your discriminant is greater than 0 and f(x(x) is greater than 0, then you have a local minimum. okay? And then if your discriminant, this big thing here, fxx times fyy minus fxy squared, if that discriminant is less than 0, then you have a saddle point. And it turns out with that one, you don't even need to look at fxx. Notice it just says if your discriminant is less than 0, you have a saddle point. And then the last case is if your discriminant is equal to 0. So this is the worst case, because if your discriminant equals 0, then the test is inconclusive, which means you don't know whether it's a local max, a local min, or a saddle point. Or it could be none of those. So you don't really know. But fortunately in your homework, none of the discriminants equal 0, so you won't have to deal with it. But I did want to bring it up because it can happen. And it can be frustrating because you do a lot of work and then you find that the test is inconclusive. Okay, so we got 4 cases there. Local max, local min, saddle point, or the test is inconclusive. And all those are mostly based on the discriminant. Now, I'm calling it the discriminant. That's the name for it. It has another name, though. So, this thing, fxx times fyy minus fxy squared, that's the discriminant. Some people also call it the Hessian. And what it is it's actually the determinant of this 2x2 matrix. It's the determinant of the 2x2 matrix, which is fxx, fxy, fxy, fyy. Okay, so this is another way of memorizing it, is remembering that it's the determinant of this thing. But it's very helpful because even though it's a lot of work to calculate, it enables you to determine whether a critical point is a local max, a local min, a saddle point, or if you can't figure anything out, then the test is inconclusive. Now, because these problems are so long, I'll probably only do 1 or 2 of them, maybe even just 1 of them. Okay, so let's see an example. Okay, example. Find all the local max. So find all the local maxima, local minima, and saddle points of the function. Find all the local maxima, local minima, and saddle points of the function. Okay? And here our function, it's always going to be a function of 2 variables on your homework. And here our function is f of x comma y equals negative 7x squared minus 2xy minus 8y squared plus 64x minus 38y plus 2. Negative 7x squared minus 2xy minus 8y squared plus 64x minus 38y plus 2. The function is so big I'm having trouble writing the whole thing on the screen. Okay, so let me just zoom out a little bit. There we go. Okay, so we want to find all the extreme values is basically what they're asking for. And in order to do that, we're going to use all this information up here. So obviously first we're going to have to find the critical points. And the way we find the critical points is we take the first derivative of each and set each of them equal to 0. And that will enable us to find any critical points. Okay, so critical points. Well, the thing is, to do the critical points, you're going to need f sub x and f sub y, and you need to set them both equal to 0. Alright, so obviously we're going to have to calculate f sub x and f sub y. So let's start with f sub x. So that's the same as partial f, partial x. So that means the other variable y is constant. So taking the derivative of this big function, we can see that the derivative of negative 7x squared, if we bring the 2 out front, is going to be negative 14x. And then the derivative of negative 2xy, where y is constant, it's just going to be negative 2y. Okay? The derivative of negative 8y squared, because for all these y is constant, we're just basically ignoring the y's. So the derivative of negative 8y squared is going to be 0. Since y is constant, negative 8y squared is constant. Okay, and then we have the derivative of 64x, which is just 64. So we have plus 64. And then because y is constant, negative 38y is constant, and so is 2. So the derivative of these last two terms is 0. So that means f sub x is equal to negative 14x minus 2y plus 64. Okay, and now we do the same thing for f sub y, or partial f, partial y. And remember, with partial derivatives, the other variable is always constant. So here, the other variable is x, so x is going to be constant. Okay, so since x is constant, the derivative of negative 7x squared is 0, because the derivative of a constant is 0. The derivative of negative 2xy, well, the y is going to go away, so we're just left with negative 2x. Okay? And then the derivative of negative 8y squared, if I use the power rule, I can bring the 2 out front and decrease the exponent by 1. So we're going to have negative 8 times 2 is negative 16y. And then, since x is constant, the derivative of 64x is 0. And then the derivative of negative 38y is just going to be negative 38. Okay? And of course, the derivative of 2, because 2 is a constant, is 0. So f sub y equals negative 2x minus 16y minus 38. Okay? And then to find the critical points, we want to set each of these equal to 0 and solve for x and y. Okay, so I'm setting each of these equal to 0. Alright, and then with these, you basically just have a system of equations. Okay, and the way you solve a system of equations is either by elimination or substitution. And most people like to do elimination or the addition method, because you can just multiply each equation by a number, so that when you add the two equations, one of the variables goes away. So what I'm saying is, we have this system of equations now. It's negative 14x minus 2y equals, if I subtract 64 from both sides, I get negative 64. And then the other equation is going to be negative 2x minus 16y equals, adding 38 to both sides, I get positive 38. Okay, so this is our system of equations. I got that from f sub x and f sub y. And then I can just multiply the second equation by something so that the x's are going to cancel out. Okay, so in particular, we know that 2 times 7 is 14, but we want them to be opposite signs. So we're actually going to multiply the second equation by negative 7. Okay, so multiply the second equation by negative 7. Okay, so what's that going to give us? Well then, the system is now going to be, the first equation is the same. It's still negative 14x minus 2y equals negative 64. But the second equation, distributing the negative 7, we actually get positive 14x plus 7 times 16. If you can't do that in your head, just, pop your calculator out. 7 times 16 is 112. So we have 14x plus 112y equals 38 times negative 7. So again, with a calculator, 38 times 7 gives you 266, but it's negative, so it's negative 266. All right, and then now we can just add these equations straight down. Okay, so we'll just add these, and that'll get rid of x. All right, so what are we going to have? We're going to have 112y minus 2y is 110y on the left side. And then on the right side, negative 64 minus 266. Again, if you're feeling lazy, just type it in your calculator. 64 plus 266 is 330. But it's negative, so it's going to be negative 330. And then I divide both sides by 110. So I get y equals negative 330 divided by 110, which is the same as negative 3. Okay, so y equals negative 3. And now we just need to find x. So to find x, we can take one of these original equations and plug in y and then solve for x. So I'm going to go ahead and take the first equation up here. So I'm going to plug in y equals negative 3 into this very first equation. I'm replacing that y with negative 3. So what does that give me? Well, just plugging in there, we're going to get negative 14x minus 2 times negative 3 equals negative 64. Okay? And then negative 2 times negative 3 is positive 6. So we have negative 14x plus 6 equals negative 64. And then we want to isolate x. So to isolate x, we'll get rid of the 6 by subtracting 6 from both sides. So that gives us negative 14x equals negative 70. And then if we divide both sides by negative 14, we actually get x equals negative 70 divided by negative 14. And if you want, you can type that into your calculator. So 70 divided by 14 is 5, if you can't do it in your head. And the minuses cancel, so we get x equals positive 5. Okay? So now we have x and y. And because we solved these, we only got one critical point. And this critical point is going to be the point 5 for x and negative 3 for y. Okay, so our critical point is going to be 5 comma negative 3. X is 5, y is negative 3. All right, and then what we have to do now is we have to use the second derivative test at this critical point, 5 comma negative 3, to decide whether it's a local max, a local min, or a saddle point. Okay? So for the second derivative test, we're going to need to calculate the second derivatives. So we already calculated fx and fy, right? But now we need to calculate, in order to use the Hessian, or the discriminant, we have to calculate fxx, fyy, and fxy. Okay? So we're going to calculate our second derivatives now. Okay, so second derivatives. Let's go ahead and calculate those. So for starters, we can calculate fxx. So for fxx, we take fx and we take the derivative of that with respect to x, and y is constant. So taking the derivative of this one with respect to x, this is all constant, so it becomes 0, and then the x goes away, so we actually just get negative 14. Okay, so f(x)(x) is negative 14. And then we also need to calculate the other second derivative. So the other one we need is fyy. So for fyy, we take fy and we take the derivative with respect to y. Okay, so the derivative with respect to y here means x is constant. So this goes to 0, that goes to 0, and this y goes away. So fyy is just going to be negative 16. Okay, so fyy is negative 16. And then the last derivative we need is fxy. And remember, fxy is the same as fyx. We learned about that in one of our discussion boards. For the second derivatives, the mixed second derivatives are the same. So fxy is always the same as fyx. That's just how it works out. So to do fxy, we can just take fx and then take the derivative with respect to y. Okay, so here's fx, and we take the derivative with respect to y. So x is constant. Okay, so this is going to go to 0, that's going to go to 0, and then this y is going to go away, and we just get negative 2. And you'll notice if you do fyx, you should get the same thing. So if we did fyx, we take this one and take the derivative with respect to x, we also get negative 2. But that's what we learned in that discussion board, so you already should know about that. Okay, so now we have our second derivatives. So we're ready to write down the discriminant. So let's write down the discriminant, also known as the Hessian. So the discriminant says you've got this thing right here, the Hessian, which is the determinant of this matrix. So it's fxx, fyy minus fxy squared. Okay, so we got fxx, fyy minus fxy squared. So plugging everything in, we've got negative 14 times negative 16 minus negative 2 squared. And really all we care about is we need to determine whether this is positive or negative for the second derivative test. Okay, so these two minuses cancel out. And this minus over here cancels out because it's a square, but there's still a minus out front. So what we really have here is 14 times 16. I know I'm lazy for using my calculator. 14 times 16 is 224. So we've got 224 minus 2 squared, everyone should know is 4. So I have 224 minus 4, which is 220. Okay, that's our discriminant. And we all know that 220 is a positive number, so that means our discriminant is greater than 0. Okay. And we also see that our fxx, which is the other thing we're supposed to look at, fxx is negative 14, which is less than 0. Okay? So we're looking at the case where fxx is less than 0, and then the discriminant, fxx fyy minus fxy squared, is greater than 0. So let's go ahead and look at our 4 different cases and decide which one is this. Okay, so going way back up here, we say fxx is less than 0 and the discriminant is greater than 0. That means you have a local max. But if you ever get a discriminant that's less than 0, remember that's a saddle point. Okay, but this one's greater than 0, and so therefore this is a local maximum. Okay, so we have a local maximum at our critical point, and our critical point we said was 5, -3. Okay, so at 5, -3. And when they have you do this, they also want you to determine the value of the function at that critical point. Okay? So we need to find the value of f at the critical point. Okay, so find the value of f at 5, -3. So how do you do that? Well, it's actually very easy. You just plug in. So we need to find f of 5, -3. That's x, y. So plugging into the original function, which is way back up here. So the original function was -7x squared minus 2xy minus all that. Okay, so we're going to be doing f of 5, -3. So we're going to be plugging in x is 5 and y is -3. So plugging that in here, we get -7 times 5 squared minus 2 times 5 times -3. Okay, minus 8 times -3 squared. Okay, so minus 8 times -3 squared plus 64 times 5 plus 64 times 5 minus 38 times -3 plus 2. It's really a huge mess here. Okay, plus 2. So this you probably want to do on a calculator, but I'm going to go ahead and write it out because it doesn't take that long. So for starters, we got 5 squared is 25. And then -7 times 25 is going to be -175, right? And then here the minuses cancel. 2 times 5 is 10, and 10 times 3 is 30. So we have -175 plus 30. And then over here, the minuses cancel with the square. 3 squared is 9. And then -8 times 9 is going to be -72. All right, and then for 64 times 5, I don't remember that one from my times table, so I'll just type it in. 64 times 5 is 320. So we have plus 320. And then -38 times -3, the minuses cancel. And then 38 times 3, I could probably do in my head, but I'll type it out anyway. 38 times 3 is 114. So we have plus 114 plus 2. Okay, and then we can just type all this into our calculator. Okay, so we've got -175 plus 30 minus 72 plus 320 plus 114 plus 2. So I got 219. And that's what they got on my math lab too, so we're good. Okay, so actually, let me write that in black. Okay. So what is this thing that we found here? This is the value of f at the critical point 5, -3. So they actually want you to calculate that as well as the critical point. All right, and we know that that is a local maximum. Okay, pretty cool. So I think that one example should be good. For your homework, a lot of these problems are very similar. They look like a similar function to this one. It's just some of the terms are negative, other ones are positive. But you're basically going to be following all these steps. And then you're just going to break it down into which case you are here. And based on which case you have, that's how you'll know whether it's a local max, a local minimum, a saddle point, or the test is inconclusive. But like I said, for your homework, none of them has the test as inconclusive. So you're not going to have to worry about that one. So it's just going to be these first three. Okay? Thanks for watching.